Here is the counterintuitive truth about quantum computing in 2026. More qubits is not the bottleneck. The bottleneck is everything around the qubits and the way we measure progress. Most practical machines today are still noisy. They run finite depth circuits for limited durations before errors wash out the signal. So performance depends on noise, circuit depth, sampling cost, and statistical confidence, not on the headline number of physical qubits in a press release. That shift in perspective changes how leaders should allocate capital. It also changes how you should interpret claims of quantum advantage. A result can look impressive while quietly depending on a noise model or a sampling assumption, or on a classical baseline that is not the best available method. Start with a simple frame. Quantum computation is about controlling quantum states, applying quantum gates, using entanglement, then measuring outcomes. In principle, that can execute algorithms with an information processing structure that classical methods cannot efficiently reproduce. In practice, today's systems are constrained by decoherence, control noise, and measurement error. Then comes the big tax, converting fragile physical qubits into reliable logical qubits. That conversion is not a footnote. Quantum error correction, or QEC, is the central architectural requirement for scalable quantum computation. If you remember one thing, remember this. A strategically durable quantum computer is not defined by spectacular device behavior. It is defined by whether physical operations can be embedded inside error-corrected logical operations. QEC is not new, or speculative, or lightly sketched. It has a deep, peer-reviewed foundation, going back decades. By 1998, there was already a canonical review treatment of code-based protection and fault tolerance framing. By 2012, the error correction formalism was codified in a standard reference chapter that many teams still use. Since then, repeated consolidations have reinforced the same message. Scaling is a systems engineering story built around codes, syndromes, decoding, and feedback control. That brings us to the first high-impact finding for strategy. Procurement should compare task-level performance under realistic noise, not platform narratives. If a vendor shows you a benchmark, your first question is not, how many qubits? Your first question is, what task, under what noise, at what confidence, with what sampling cost? If you cannot connect the experiment to a decision-relevant workload, it is not procurement evidence. It is marketing input, and it should be treated as such. One tool that illustrates this is Fisher information analysis applied to noisy intermediate-scale quantum applications. The important point is not the math. It forces you to ask what quantity is being estimated, how noise degrades it, and how many samples you need. In other words, it pushes evaluation toward outcomes you can audit. The second finding is about programmability, and it surprises many executives. Hardware-aware programming is already operationally relevant, even before full fault tolerance. A concrete example is ease-gate programming on trapped ion hardware, demonstrated in 2022. The takeaway is that native gate design, plus compiler and control co-design, can materially change what is executable. Sometimes the fastest path to better results is not a new device. It is a better mapping from algorithm to the device's native operations. This matters because quantum proposals often assume an abstract, uniform machine. Real devices are not uniform. Different substrates have different native operations, different noise structure, and different calibration realities. So the compiler is not just a convenience layer, it is part of the machine. Now the third finding, which is where many roadmaps become vague. The physics of information bottleneck is a combined stack. State preparation, coherent control, measurement fidelity, error correction circuitry, decoding latency, and finally workload-specific algorithm design. Any one of these can break the chain. Decoding latency deserves special attention for planners. Error correction is not only about having a code on paper. It is about extracting syndrome information, decoding it fast enough, and feeding back corrections. That is real-time systems engineering. It touches control electronics, timing budgets, and integration with the rest of the compute stack. If a scaling claim does not include those assumptions, it is incomplete. The fourth finding is about algorithms, and it is the antidote to universal hype. Algorithm work splits into near-term noisy methods and fault-tolerant methods. Surveys tend to emphasize structured workloads, not general speed-up across computing. Think quantum simulation, linear algebraic primitives, and optimization-related subroutines. Also think hybrid quantum classical workflows, where a quantum device acts as an accelerator. That word, accelerator, should sit at the center of your strategic model. Classical compute remains the default substrate for most production workloads. Quantum, if it becomes useful, will likely be a specialized layer, high value, high constraint, and tightly integrated with classical high-performance computing. So a practical leadership question becomes, where is the boundary? Which part of the workflow runs on the quantum system? How does data move in and out? How is output verified? And what economic value is created, given the overhead? Verification is another quiet constraint. For many workloads, you must be able to check results to use them operationally. If verification is as expensive as the computation, advantage evaporates. That is why disciplined workload selection is not optional. It is the price of admission. The fifth finding is about optionality across hardware substrates. Today, there is real competition among superconducting circuits, trapped ions, photonics, and neutral atoms. There are also distinct paths like quantum annealing, aimed at optimization-specific systems. Fault-tolerant scaling may favor different architectures than near-term demonstrations. So long-horizon strategy should avoid premature monocultures. From a mapping perspective, you can see the ecosystem clearly. Commercial system builders include IBM and Google in superconducting approaches, Quantinuum and IonQ in trapped ions, PsiQuantum and Xanadu in photonics, Quera and Pascal in neutral atoms, D-Wave in annealing and hybrid optimization. Governments and standards bodies matter just as much as vendors. The United States National Quantum Initiative is a coordination layer across agencies and labs. NIST anchors measurement science and adjacent security transition work. The Department of Energy National Laboratories connect devices, algorithms, and high-performance computing integration. The UK and the European Union run national-scale programs through the UK National Quantum Technologies Programme and the European Quantum Flagship. International standardization bodies like ISO and IEC sit in the background, shaping interoperability and terminology. Why should an investor or sovereign strategist care about standards this early? Because coordination ceilings can delay adoption, even when hardware improves. Procurement language, benchmarking norms, and security transition timing can become the limiting factor, not physics. Now bring the horizon into focus. Near term, from 2026 to 2050, expect noise-aware experimentation, expect hardware-aware compilation gains, expect early QEC demonstrations, and better measurement discipline. In that band, credibility comes from reproducible task-level advantage under realistic noise. It also comes from transparent physical to logical assumptions, not hand-waving. Midterm, from 2050 to 2100, is conditional. If overhead falls and logical operations become reliable enough, quantum accelerators may become high-value infrastructure, likely in simulation, some optimization workflows, cryptanalysis relevant risk modeling, and scientific discovery pipelines. But the gate is QEC overhead and integration, not raw device spectacle. Long and deep bands remain contingent. Even a mature quantum sector is more likely to be a specialized layer than a universal replacement. Value concentrates where the workload is physics native, or information theoretic, and verification is tractable. Anything that assumes routine general-purpose quantum computing across most enterprise workloads remains speculative. That leads to the practical operating model for leaders today. Avoid two false procurement models. First, buy qubits, receive advantage. Second, wait until quantum is fully mature, then adapt. The workable model is small but technically competent readiness. Readiness looks like an auditable capability stack, task-level benchmarking under realistic noise, hardware-aware compilation literacy, QEC due diligence, including syndrome extraction and decoding assumptions, post-quantum cryptography migration planning, because the security transition is a coordination decision, and a cross-platform workforce, so you can move when inflection points arrive. When you hear a scaling claim, ask a few sharpening questions internally. Which workload would we run? And what classical baseline would we use? What noise-aware metric would decide whether we change a budget? Which evidence would make the claim credible? Physical error rates, logical error rates, overhead, latency, or independent reproduction? And finally, does the workload survive the overhead once error correction is included? Quantum computation is not a bet on faster computers. It is a bet on reliability, measurement discipline, and workload fit in a world where information is physical.